Okay, hello and welcome to this third module of the workshop, which is, as you can see, atomistic simulations. My colleagues here, Professor Field and Professor Messervich, over the past few lectures have introduced you to microstructure, qualification, quantification, and looked at some of the theoretical methods at mesoscale in understanding microstructure and their evolution. What I will be covering over the today's lecture and next few lectures is at a somewhat lower length scale and time scale, looking at atomistic simulations and how we can leverage these for many different applications. So the idea is I will show you through examples that these methods, including density functional theory to ab initio molecular dynamics and molecular dynamics simulations, can address a multitude of properties, processing, and structure correlation in material space, and give you examples and the relevant theory. So let's get started. Hopefully I can keep you awake for this. Photo of our pretty campus here, WSU. This is our campus in Pullman, Washington. And here is where my research lab, the computational nanoscience lab, is located in a building called Sloan Hall. And so the question is, what do we do at computational nanoscience lab? So our goal, this is a busy slide. Our goal is to address the energy challenge, that is coming up with more efficient energy conversion and storage devices to address the energy challenge, and renewable energy devices, which requires identification of tailored materials with tailored properties that can be used as components in these devices, and also to understand how they can be processed to come up with those tailored properties that are required for these materials to be employed in some of these devices. So over the years, we have done quite a bit of work in energy storage. So you can see here at the top some of the energy storage applications, looking at batteries primarily. Obviously, energy storage can be fuel cells, batteries, capacitors. Our work has looked at many different battery technologies over the years. We have model systems relevant to lithium-ion batteries, lithium-air batteries, and sodium-ion batteries more recently. Mostly looking at processes involving ion transport at interfaces, ion transport through the electrolyte medium, the chemistry and and electrochemistry at interfaces, and various other properties of the electrolyte itself. A lot of this work has gone into identifying various classes of electrolytes, which I'll be talking about and introducing you today in the lecture, including ionic liquid-based electrolytes and various amorphous sodium sulfur-based electrolytes such as sodium thiophosphate and sodium thiosilicates. Besides that, we have also done quite a bit of work in various thin film photovoltaic solar cell technologies. We have addressed challenges in the domain of a couple of different variants in photovoltaic solar cells, including organic photovoltaic solar cells, hybrid perovskite-based solar cells, which are pretty new and have shown great promise. And more recently, we have also done some modeling-based work to address challenges in cadmium telluride-based solar cells. So what have we done in the solar cells space with atomistic simulations? Well, number one, we've characterized, or we've calculated space with atomistic simulations of some of these materials. Number one, we have characterized, or we've calculated space with atomistic simulations. Looked at impact of number one, we have what have characterized, or we've calculated space with atomistic simulations. Looked at impact of number one, we have what have characterized, or we've calculated space with atomistic simulations. Looked at impact of number one, we have what have characterized, or we've calculated space with atomistic simulations. Obviously, you have to identify the sites where you have to characterize the morphology of these layers, and how get to the morphology of these layers to address challenges at much larger So we have scaled up our work using methods called Monte Carlo, which lends us to look at morphologies of the order in length scales of tens of micrometers and time scales of microseconds. again, I mean, these applications are geared towards identifying tailored materials for some of these applications, but what is very important is how do you process these? For example, how do you process thin films to get a tailored morphology? So we have done a lot of modeling work, mostly atomistic simulations looking at the morphology of thin films grown out of solvent-based processing. More recently, we have looked at extraction of metals such as aluminum, magnesium, sodium, etc., that can be from lunar and Martian regolith, which is the soil on the moon or Mars, and which can be used for additive manufacture of various parts. So to sum this up, basically our lab, like I mentioned, have focused on the energy challenge, looking at energy conversion, storage devices, and processing of materials, and establishing some sort of a correlation between the processing conditions with the structure and functional properties of these materials. The methods we have used are like density functional theory based calculations at the smallest length scales, to ab initio molecular dynamics, to classical molecular dynamics and Monte Carlo. More recently, we have employed data science or machine learning based methods to speed up and do high throughput screening of materials for various applications. And the classes of materials, as a theorist, we can our work can span over a larger domain of materials. So we have done quite a bit of work not only with metal alloys but with ceramics, these perovskites, amorphous materials, wide bandgap semiconductors, as well as some very interesting molten salts and ionic liquids. Okay, so the holy grail of this computational work, so to speak, is, like I mentioned, to correlate the processing conditions for various applications to the material structure that it generates, and finally what sort of functional properties that it leads to. So I'm just taking this image out of a recent paper that reviews some of these physics-based models, which in combination with data science or machine learning approach can really speed up the process. So this particular paper looks at applications in additive manufacturing, which is very, and how do you establish correlation between the processing condition with the additively manufactured part, in this case, involving both data generated from experiments and characterization, which you have heard quite a bit over the past week, as well as physics-based models at multiple length scales, going all the way from atomistic simulations to mesoscale to continuum-based methods, such as finite elements models or computational fluid dynamics, to look at some of the thermofluidic aspects, and then use data science for all the data gathered from these experimentation and modeling to learn about the various correlations and trends in this, and ultimately get the desired structure and properties in the additively manufactured part. So while this particular paper looks at additive manufacturing, the same sort of process can be applied to many different methods and applications. So I just mentioned theory across various length scales, and this is a slide probably, or a variant of this is something you might have seen in the past, but this is a good introduction to kind of the different length scales and time scales that some of these methods can investigate. So we start from the bottom left corner, which looks at the smallest length and time scale. So if you look at the length scale, it's a logarithmic scale, of course. We are talking about angstroms, or 10 raised to negative 10 meters, and time scales of the order of picoseconds. We're talking about ab initio or first principles methods, namely one of the most popular ones is density functional theory, though density functional theory doesn't capture time aspects, it just minimizes structures. So density functional theory is a quantum mechanics based method, which basically solves a modified version of the Schrodinger's equation, and it can calculate a wide range of properties, including electronic structure of materials. It is widely applied for finding absorption energies or various sort of free energies, for example, in catalysis, absorption of atoms on top of catalyst surfaces and energy barriers thereof. So density functional theory is very popular in materials science for doing static calculations at 0 Kelvin to find the most energetically favorable structures of materials, calculate lattice parameters and materials properties. The next higher scale up, like I mentioned, one of the challenges with just purely density functional theory, even though it's fairly accurate, is that we are limited to very tiny length scales. We are talking about hundreds of atoms, and so therefore, and also 0 Kelvin temperature. So if you wanted to capture the dynamics and calculate properties such as like transport coefficients, such as diffusion coefficients, and transport properties such as thermal conductivity, and scale up, the next higher ordered method is what is called ab initio molecular dynamics. So ab initio molecular dynamics is still related to relatively small systems, but what it can do is it can evolve the structure with time, and so you can study dynamic processes happening at small length scales, and it is still capturing the accuracy of the density functional theory based calculations, because it doesn't require you to specify an empirical pair potential, which is required of classical molecular dynamics. So it's very effective when the interaction potentials in a certain system are not known or very complicated to parameterize. And you will see plenty of applications of ab initio MD in my presentation over the next few days, including some of my work with the battery electrolytes, looking at sodium ion transport through these amorphous structures. We have employed quite a bit of ab initio MD for that. The next method, which can capture effectively much larger length scale, we are talking about up to millions of atoms and up to hundreds of nanoseconds of simulation time, is called what is called classical molecular dynamics simulation. It's called classical because it basically is a solver for the classical Newtonian mechanics applied to a system of atoms, and is based off its principles or background theory is based off statistical mechanics or statistical thermodynamics, which I will introduce in my lecture tomorrow. So basically, if you have an ensemble of atoms, which is true for most materials we look at, can we evolve it over time, and under certain conditions can we assume that averages of these properties in their microstates can give us reliable values of their characteristic properties at larger length scale. So that is what classical molecular dynamics enables, and it is able to calculate a wide range of properties, including viscosity, thermal conductivity, looking at structure, relating it to other properties, and very effective. It can also look at phenomena happening at interfaces, for example, ion transport, electron transport, if you are doing ab initio molecular dynamics. So that is, and capture the dynamics of that process. But it is still not able to scale up to beyond, like I mentioned, about 100 nanometers with the best computers we have today. So which is essentially not enough for microstructures if you wanted to look at it. So when that happens, sometimes to get around that, the method we apply is what is called coarse grained molecular dynamics, which is up in the next in terms of the time scale and length scale that it can access. Coarse grained molecular dynamics is not at an atomistic resolution. It basically defines beads that comprise multiple atoms or moieties as a single bead, and therefore you can scale up to much larger systems. It is not used as much in metallic systems or ceramics, but it is used quite a bit if you're working with polymers. So in the polymers community, coarse grained simulations are quite routine to access much larger size molecules that polymers are. It's also used in biochemical systems, such as if you're modeling proteins and other materials of that nature. Obviously, beyond that are some of the models that you have heard of quite a bit in a lot of details this week, mesoscale methods, including phase field. There are quite a few different approaches here. Phase field is one of the popular ones, of course. And finally, continuum-based theory, such as finite element models, or if you're looking at liquid systems, computational fluid dynamics, which solve continuum mechanics equations. So the key is, a lot of times, as you will see again from examples that I present here, one approach is simply not enough to solve a certain challenge in the material space. If you're trying to come up with material selection for a certain application, or looking at addressing a physical phenomena that's happening at large length scale, and yet want to capture the accuracy that you get from the granularity at small length scale, one approach just doesn't work. And this is something we have applied and seen in a lot of applications, including this one here, which I will introduce in a little bit more details in a couple of slides. But what I want to get here is, this slide shows how do we predict the overall performance of a system such as a battery, which is at a macro scale. We are talking about a battery cell, while capturing some of the detailed ion transport, etc., and solubility of chemical species, the chemical stability aspects that is captured only by quantum mechanical approaches such as DFT or molecular dynamic simulations. So, as you will see in this example, where we try to identify certain types of electrolytes known as ionic liquids using a wide range of approach, where some of these at certain length scale, for example, density functional theory was used to capture electron transfer reactions happening at interfaces, which is you have to apply quantum mechanics level theory for that. Two, capturing thermophysical properties of these electrolytes such as ionic conductivity or their ability to dissolve and diffuse lithium ions, which can be captured using molecular dynamic simulations. Two, a continuum based theory, which is then able to scale that up and fit those calculated properties and coefficient to a continuum length scale model, solving basically Poisson's equation to get the voltage, basically the electrical potential across the cell, and also look at the transport across the battery length scale, from which you can then predict things like the current voltage characteristics of the battery that can directly be compared and validated against experiments. And then in case of a liquid electrolyte, the electrochemical stability becomes very important. So, even if you have an electrolyte that performs pretty well in terms of their current voltage characteristics, they may not be durable. So, at that point you have to also test how durable your electrolyte is by doing calculations at quantum mechanics level to calculate the electrochemical stability of these electrolytes. So, it is basically jumping across a wide range of length scales and time scales to capture the overall performance of a cell, while capturing the resolution of physics at extremely small length scale. So, like I mentioned in the previous slide, so these are some of the work we have done for towards this particular application, where we started with density functional theory level calculations to look at electron transfer reactions, to diffusion and transport processes captured through molecular dynamic simulations, and finally continuum length scale calculations that were able to predict the current voltage performance. In fact, one of the things that we found from this project was that at a slightly elevated temperature, these ionic liquids achieved a really good specific capacity, which later on was validated by experimentalists by making a cell and testing it out. So, that was pretty satisfying by being able to look at theory at different length scales and be able to effectively predict the performance. So, today a lot of focus is on high throughput screening and tailoring of materials for various applications. There is the materials project, where one of the goals of it is to kind of developing a database of properties of commonly applied materials for various applications. So, even for that purpose, there are a couple of approaches that you can apply. One is a purely physics based approach, which is, for example, the ionic liquid battery application that I mentioned. At the end, you have many different electrolyte formulations, and one of the questions is, what is the electrochemical stability of these chemicals? And you can apply the density functional theory approach with a high throughput method to calculate the frontier orbital energies, which are called the HOMO-LUMO energies, from which you can have a pretty good estimate of what is the width of the electrochemical stability window across which this electrolyte is able to operate, and from which you can down select electrolytes for these applications. But what is becoming more and more common to apply today flammable, they're easy to catch fire. So there's a lot of work going on in alternate technologies that are known as beyond lithium ion, including lithium sulfur, lithium air, sodium ion batteries, etc. The main goal being making these batteries even more durable, specifically if you wanted to apply them outdoors for energy storage with wind farms, etc., and also to make them cheaper, which lithium ion batteries are still not the cheapest ones. So how do these lithium ion batteries work? Well, the principle of operation is pretty straightforward actually. You have these three components, the anode, the cathode, which are the two electrodes that are separated with electrolyte and separator. Typically, like I mentioned, the standard electrolyte is liquid based, organic liquid based electrolyte that is used. The chemistry of the anode and cathode can be varied, and there are many different chemistry that are being explored or even commercialized. The standard being a graphitic anode. So what happens at the anode, which is the negative electrode, is the lithium ions are basically stored in there as lithium atoms. And when you connect the battery to a load, let's say, so that there is a requirement for current, these lithium ions are oxidized to lithium ions, and the electron flows through the external circuit, and the lithium ion goes through the electrolyte and separator and gets embedded, or what is called intercalated, in the cathode structure. Okay. The cathode structure can be made of many different materials. This one here shows lithium cobalt oxide. There is lithium nickel oxide, mixed oxides including cobalt, nickel, etc., and then spinels, lithium manganese oxides, which are cubic structures. And so spinels and layered electrolytes, cathodes are the most popular ones. And the lithium ion basically during discharge process gets intercalated within that cathode structure until all of the lithium ion is depleted when your battery is completely discharged. At that point, you connect it again with an external circuit to supply the electrons back to the system, so that the lithium atoms are again ionized and flow backwards towards the anode and get stored there for another cycle of discharge. So that's how the battery operates. But there are many different very interesting chemistry and electrochemistry involved here. It's a multiphysics problem here, really, of how the lithium ion ionizes or oxidizes, how effectively, how much of it you can store inside each of these electrodes, and how efficiently they can be transported through the electrolyte that separates them. So if at a high level, if you wanted to look at the performance of a battery, you have this spider chart type of diagram where you're looking at all the different metric that goes all the way from cost, which is obviously very important, to how long their calendar life is at a certain temperature, their cycle life, how many cycles they run. So calendar life and cycle life are a little different. Cycle life is how many charge discharge cycles a battery is going through, while calendar life is, even if you're not charging discharging them, how long does it last and stay stable. There is safety, of course, which is a very important metric, right? The peak amount of power that it generates, the energy density, and specific energy, which is energy density is the energy stored per unit volume, while specific energy is per unit mass, because for some applications, let's say aerospace or some application, you might be constrained in terms of space, so the per volume metric might be very important there. In other applications such as transportation or in electric vehicles, the specific energy is obviously very important. Okay. So I mentioned briefly that there are many different technologies. You see this pie chart, 3D pie chart, where at the top you see commercially deployed systems today, where 68% of it, about 70%, is lithium ion, and the rest of it are many other technologies, of which the prominent ones are there's some lead acid batteries that still used. There's redox flow batteries. Redox flow batteries are used quite a bit in renewable energy storage systems. And then there is sodium based batteries. So we have done quite a bit of sodium based battery work, and I will introduce that in a moment. Why is sodium important? Because obviously sodium is an earth abundant material. We have about 1,000 times more sodium in the earth's crust than lithium, so it will be wonderful if you were able to simply use sodium for these applications. Okay. So one of the very promising technologies of all the ones that I showed you in the previous slide is what is called the all solid state battery. This is being studied and explored for automobile battery applications as well, and it's quite a way, far advanced in that. So what are solid state batteries? As the name suggests, these batteries, all components of these batteries are at the solid phase, including the electrolyte, because any battery, the electrodes are obviously solid. In this case, the electrolytes are also made of solid materials, could be crystalline, amorphous. We'll look at some examples in the next slide. It's very promising as a next generation storage because primarily they are very thin, so you can achieve, you can use an electrolyte which is a thin film, so they are relatively small dimensions, and they are very safe because you don't have electrolytes that are volatile. So, that achieves quite a bit of high safety here. And then the energy density of these solid state batteries is also has improved quite a bit. They are not yet comparable to the standard lithium ion, but it's getting there. So this chart here shows you a couple of metric which kind of measures the performance of a energy storage system. So on the y-axis you have the discharge voltage, and then on the x-axis you have specific capacity. Roughly a product of these two gives you what is called a specific energy. So these curves are different specific energies, 300, 500, 700. The higher it is, the better. And you can see that some of these sodium ion batteries are now achieving up to about 500 watt hours per kilogram of specific capacity, which is actually getting comparable to some of the standard lithium ion ones. So there's a lot of promise for this solid state battery technology. So once again, why sodium, why not lithium? Besides the fact that the main driver obviously is that sodium is earth abundant, and therefore that would drive down the cost for these batteries quite a bit. So that is a huge driver in promoting this technology, but also some of the initial modeling and theory based results show a faster kinetics for these sodium ion batteries at the electrode and less propensity for what is one of the major challenges in these technologies, dendritic growth. But it's still in the early stages. We don't have a full understanding of the dendritic growth process with sodium based batteries. So the big question though, so why are they not already commercialized? What is the major challenge? One of the major challenges is what is the right material to use as an electrolyte for these batteries, right? You have a solid state battery with a solid state electrolyte, but what sort of electrolytes do we use? The challenge is, compared to liquids in general, solids have what is called lower ionic conductivity. Ion conduction pathways in solids are kind of higher energy barriers and slower, therefore the diffusion of ions are lower compared to their liquid counterparts, resulting in typically lower ionic conductivity in these electrolytes. So there are two types of solid state electrolytes in general, obviously. One is crystalline, examples of which are LLZO, which is lithium lanthanum zirconium oxide, or lasicon, nasicon. There are quite a few of these electrolytes, including garnet based materials such as LLZO, that are being explored. But even for these materials, typically the ionic conductivity is of a couple of orders of magnitude lower than the liquid state electrolytes. Recently, some experimental characterization and modeling results show great promise in applying amorphous solid state electrolytes, that is basically glassy electrolytes or amorphous. There are two types of chemistries within that space. There are oxides and sulfides. So there are oxide glasses and sulfide based glasses. Initial studies show that sulfides have quite a bit higher ionic conductivity than oxide based amorphous structures, but at the same time they have some stability issues. So it's about optimizing the ionic conductivity while keeping this electrolyte stable across the interfaces with anodes so that there is no dendritic growth, right? So we have done quite a bit of work exploring solid state amorphous sulfide based electrolytes for batteries applications in conjunction with in collaboration with experimentalists. So a couple of different chemistries that we have looked at, and I'll present results over the next few days. Is one of them is the sodium thiosilicate, which is a mix of sodium sulfide and silicon sulfide based glasses. So you can play with the composition to tune the property. The major property here is the ionic conductivity. So, how can you tailor the composition of these glasses to get the highest ionic conductivity that you can achieve? That is the challenge here. To do that, the challenge with modeling these systems is, if you want to use if you want to calculate dynamic properties, you have to use either molecular dynamics or ab initio molecular dynamics, but molecular dynamics, there are no quantified or no reliable pair potentials to look at these chemical systems. So, we applied a combination of ab initio molecular dynamics, and we also came up with our own parameterized pair potential for these systems to apply classical molecular dynamics. And as I will show you in the in the next few lectures, the first step was validating our calculations with X-ray scattering data to look at the structure we have in our system that we are modeling versus the structure that is available from experiments, and it matched pretty well. We also calculated from our simulations the ionic conductivity at a range of temperatures, and they compared reasonably well within 10% of experimental data. At least we captured the trend correctly. Obviously, we did not get the exact agreement with experiments, but it captured the trend of how it varies with temperature. And we also looked at activation energies for ion hops through these systems. So, the activation energy is basically the energy barrier for ions to hop from one side to the other, and the lower this energy barrier is, obviously ion hopping is faster, and therefore, you get higher ion diffusivity, resulting in a higher ionic conductivity, which is very important to commercialize these electrolytes. We have also looked at a somewhat different class of electrolytes, or the same class of electrolytes, a different chemistry, which is based on sodium thiophosphates. These are very, very interesting systems, both sodium thiophosphate for sodium based batteries and lithium thiophosphate for lithium batteries. There are sodium thiophosphate that has 3 crystalline phases, a cubic, a tetragonal, and an orthorhombic phase. The cubic and tetragonal alpha and beta phases are stable at low temperatures or room temperatures, but their ionic conductivity is pretty low. On the other hand, some recent work shows that the orthorhombic phase, which is the gamma phase, which is not stable at room temperature, but has very high or relatively high ionic conductivity, because these comprise of PS4 tetrahedral units, and these tetrahedral units at slightly elevated temperatures show quite a bit of rotational effects. So, you can capture this from this location map here for the different ions. So, the green dot is the sodium, the yellow is the sulfur, and the orange is the phosphorus. So, basically these phosphorus sulfide PS4 tetrahedral units show rotational effects, which lead to, as I'll present in detail very soon, a very high ionic conductivity of the sodium ions, resulting in overall high ionic conductivity of these systems. Okay, so far any questions, general questions? This is again still an introduction, but feel free to ask any questions if you have any.
Ions.
Yeah, sure. We look at those defect effects. In fact, one of the reasons the amorphous structures have a higher ionic conductivity than the crystalline counterparts is because of the free volume for ion hopping that it opens up in these amorphous structures, because of a less short range and medium range order that opens up new ion hop pathways. And there is a theory based on the Anderson-Stewart model, which predicts the ionic conductivity as a function of the ion hop distance, the shear modulus, and something that is called a doorway radius. And the doorway radius for these become quite a bit higher when they are in the amorphous phase, and therefore that leads to enhanced ionic conductivity. So, I'll show you some results later of how it really works out for these structures. But what we are also exploring and also being synthesized and tested is what is called glass ceramics for these. Any other questions? Okay. The other class or other technology that we have modeled or looked at quite a bit over the past several years is photovoltaic solar cells. So, I'll just do a brief introduction of thin film photovoltaic solar cell technologies. This chart is very familiar to anyone working in photovoltaics. It's published by the National Renewable Energy Lab, and it is basically the record efficiencies of various photovoltaic solar cells technologies over the years. So, it kind of shows the time evolution of the efficiencies of various technologies. The most prominent one, which is mostly the commercialized one, is the crystalline and silicon solar cells. So, you can see these blue squares here showing how those efficiencies are going over time. There is cadmium telluride solar cell, which is also commercialized to a certain extent. So, you see these the green circles with yellow filling in here. So, that is cadmium telluride. And then there are some, both these technologies, silicon and cadmium telluride, have been around for a long time, since at least the 80s. There are some emerging technologies on the other hand. For example, the yellow, the red circles, if you can see these with yellow filled circles, is perovskite solar cells. So, these are thin film solar cells that we have modeled quite a bit, and I will introduce in a moment, and organic photovoltaic solar cells. So, perovskite solar cells over the past decade or so have shown remarkable improvement in what is called the power conversion efficiency. The power conversion efficiency has gone all the way up from 4% in 2009 to right now the highest recorded efficiency is about 26%. So, that has been pretty remarkable improvement in a short duration of time. So, what are perovskite solar cells? A lot of you might probably know what perovskites are. Anyone? Perovskite structures and materials. So, it's of the form ABX3, where A and B are the cations and X is an anion. It's named after, I believe, a Russian mineralogist, Perovsky, who first discovered it. Initially, these were mostly inorganic perovskites, such as calcium, titanium oxide, CaTiO3, and many others. But the ones that are being used in these thin film solar cells are what is known as the hybrid organic inorganic perovskites. So, they still have the ABX3 structure, but this cation is organic. It has a methyl and ammonium group, and CH3 and H3, methyl ammonium. B is lead, which is a little bit of a concern. I will talk about it. And then X is iodine or a halide. It could also be, people are exploring in chlorine or other halides, but typically it's iodine. So, what is so special about methyl ammonium lead halide based perovskite for these solar cells? And their structures are shown here. It has excellent properties for photovoltaics. Number one, it has excellent photo absorption characteristics. It has a low band gap. So, there's something called a Shockley quasar limit, which predicts that solar cells with the highest efficiencies will have a band gap of about 1.3, and these materials have a band gap of about 1.57. So, they have a very appropriate band gap for these applications. They have long carrier diffusion lengths and high carrier mobility, which are all characteristics required for achieving high power conversion efficiency in thin film solar cells. So, therefore, they have become pretty popular. The way these solar cells work, they are basically stacked layer one after the other. The main absorber, which is the main material that does the conversion from solar energy to electrons and hole pairs that are generated, is the perovskite that I already talked about, the methyl ammonium lead halide. But you have to separate out the electron and hole that is generated in this absorber layer, and to do that you typically have what is called a planar heterojunction, which requires a hole transport layer. There are many different materials used for that, and then you need an electron transport layer, ETL, for transporting the electrons to the other electrode. So, again, there are very many materials that are used as both hole transport layers and electron transport layers. One of the popular ones is this C60 fullerene derivative, which is what we are interested in, and I will talk about when I present the results. So, when solar energy is incident on the absorber, like I mentioned, it has the appropriate band gap, then it can produce an electron hole pair, and the job is to kind of separate them out. Otherwise, if we can't, what happens is called non-radiative recombination, where the electrons and holes kind of recombine and they are lost. So, that is the loss in efficiency. We do not want that. So, you have to have the appropriate band structure of each of these layers to be able to promote the electrons to hop from the absorption layer to the whole electron transport layer and to the aluminum electrode ultimately, while the hole would go through the whole transport layer to the transparent indium tin oxide electrode. So, that is in a simplified way the working principle of this device. So, what are the challenges in this domain in perovskite solar cell? The major challenge is charge recombination and hysteresis due to the rough surface. So, how are these solar cells made? They are made using solvent based processing. So, coating of the lead halide perovskite, making a thin film on a substrate and then drying it out, maybe annealing it to make it better, and then these are very thin films, and then on top of it you coat the whole electron transport layer, and then you develop your solar cell. So, this solution based processing oftentimes leads to very rough interfaces between, let us say, the absorber layer and the electron transport layer, and the defects that result, such as these pinholes and structural defects, and also chemical defects such as excess halides, etc., lead to loss in efficiency and charge recombination. So, basically, if you are working in this technology, the main thing is how do you make very even and smooth thin films of these materials with a smooth interface between them. So, one of the ways that experimentally has been explored is if you add this chemical, which is called phenyl C61 butyric acid methyl ester. So, it's basically a Buckminster fullerene functionalized with a phenolic group and this esteric group. If you add this to the solvent, then some of it gets incorporated in the grain boundaries of the layer that forms this perovskite layer, and that is able to mitigate the impact of some of the common defects such as lead iodine anti-site defects. They are able to bind with the iodine, and that reduces recombination of electron holes when they are transported through these films. But it's this recipe of how you make it is kind of a magic. I mean, you try out many different, in this community you try out many different ways of making it. You vary the processing conditions, the concentration of these molecules in these solvents, and from that you get a certain film, and then you test them out and record the efficiency, and you do this kind of in a iterative way to get the best recipe to make these films. So, our effort here was to see if there is a way we can start from the very fundamentals, which is looking at the electronic structure of these layers and identify what sort of defects lead to trap states that are generated in the electronic structure, in the band structure, and what sort of impact they might have in charge recombination, and how we are able to mitigate it by tailoring the processing conditions, such as what temperature we process this at, what concentration these the PCBMs should be in the solvent, etc., to get a smooth even layer so that we are able to get the best efficiency. So, this is kind of a schematic showing the different pieces here. On the one hand, on the left you see electronic properties, which is obviously what drives the performance of these devices, and on the other hand you have the structure of the interface. We are interested in looking at what does the interface look like between these dissimilar materials. Perovskite is very different from the PCBM molecules that deposit on top of it. What is the deposition mechanism? What are the sites where the deposition happens? And then from that, can we glean into the morphology that results of these thin films? So, to answer this question at the center, the structure of the interface, we really need to know, we need to really get into the atomistic level details. So, molecular dynamics simulations is pretty appropriate to look at these thin films and the sites where deposition of these molecules happen and how they are anchored at various crystal facets of these perovskites and various terminating chemical groups. It could terminate with lead iodide groups or methyl ammonium iodide groups. How does that impact? So, these are some of the questions that we can answer using an atomistic simulation level of details, namely molecular dynamics simulations. On the other hand, if we wanted to scale up and look at morphology, MD cannot do that. We simply cannot get into micrometer and microseconds length and time scales. So, how do we do that? we use a different approach for that, which still takes inputs from our MD simulations. It's called kinetic Monte Carlo. So we first try to figure out from our MD simulation what the stable sites are for deposition, what the energies are, free energies for deposition processes, and then we can measure the rates of those processes happening. And kinetic Monte Carlo is a stochastic method that then scales up and generates the crystal growth process from those inputs from MD simulations. And I'll show you from my results here for these systems that we are able to look at both the structure of these grown layers on the perovskite substrate at large length scale. We are able to characterize the growth rates and also the quality of the films that are grown using these methods, and compare with some experimental imaging as well. On the other hand, the third aspect that needs to be addressed is the band structure itself, which is the most fundamental aspect, and pretty much the only way to do that is through electronic structure calculation, which requires the finest level of theory, which is quantum mechanical based calculations, namely DFT in this case, which lets us determine the density of states or band structure, and from which we can see what various atomistic defects can do to the band structure, whether they develop shallow level defect states or deep level trap states, and what those will do to the the electron transport and the hole transport. So this is an image that shows you a result from our MD simulations and how we extrapolate that and use that as input to develop the films that are grown using kinetic Monte Carlo. Like I mentioned, the dimensions that we simulate using MD is 10 by 10 nanometer, and we are only able to look at 60 nanoseconds. Even then, these are simulations that involve hundreds of thousands up to a million atoms and take at least a week or more to converge, right? On the other hand, Monte Carlo simulations, we are able to easily look at surfaces of sizes. In this case, the one I'm showing you is 100 by 100 nanometer, but you could get to micrometer level length scales and up to 1 microsecond time scales, and each calculation is only a few hours. So we significantly reduce the time needed for computing these. And what we can do then is because this is a stochastic model, we can run many different types of initial input structures and get some sort of an error bar estimate or uncertainty estimate of what the resulting structure is. So this efficiency in computation that kinetic Monte Carlo lends here can really be a huge advantage in exploring these structures. And finally, this one here, which again I will present the physics of it in a later lecture, but I'm just showing you some of these applications today as an introduction. Also show these that for certain processing conditions, for example, if you have 0.24 molar concentration of these particles in the solvents, you get these small crystallites or crystalline domains, while if you go for a lower concentration, that results in a slightly more amorphous layer that forms. So we can get into those, and we also compare them with similar structures that were obtained from experimentation and characterization and seem to agree pretty well. So you see this structure from here, and then we get the same sort of structures from our kinetic Monte Carlo model, which is very encouraging. Okay, it's at the hour. Do we take a short break and come back? Okay, let's do that. this perovskite layer on top of it to achieve pretty high efficiencies. I think that chart also has had some efficiencies for tandems. You can reach as high as 40 to 45% efficiency with tandem solar cells. Yeah. But the challenge with tandem is you have more interfaces, and as soon as you have more interfaces, there will be more losses, including recombination. You can get to very high theoretical efficiencies with tandems. So yeah, I mean, the photovoltaics community is certainly exploring perovskite-based tandem solar cells. Okay. We'll get to another application, which again, I'll present in the next few days as a use case or example, which is a very different class of materials. Now we are talking about alloys, which a lot of you are interested in. So in electronic packaging systems, a lot of times thin film of tin is deposited on top of copper for various reasons. It reduces oxidation and serves as a wetting enhancer during subsequent soldering for lead attachment, etc. So the challenge is when you have this deposit thin film of tin on top of the copper, it creates compressive stresses which can lead to what is observed as small whisker growths out of that surface, tin whisker growths. It's not just for tin. This has also been observed for zinc deposited on steel, or I think aluminum on silicon. So whisker growth has been a challenge, particularly in electronics packaging, because this can lead to shorting, which is a big trouble, right? So the idea is how can we reduce or completely eliminate whisker growth from these surface defect regions. So to understand that, first, what has the industry done over the years? Obviously, electronics have been around. We use them every day. So surely they have come up with a solution. Traditionally, the solution was to add a little bit of lead, about 3 to 4%, and it's not very well understood, but adding lead significantly reduces or almost nearly eliminates the formation of these whiskers from the surface. So why does this happen? To understand that, we have to understand what leads to the growth of these whiskers. What is the mechanism at play? The primary mechanism at play which causes the whiskers to grow, number one, is it needs the in-plane compressive stress, which is basically the driving potential for diffusion of tin atoms to the surface and the growth of these whiskers. It also needs a less tenacious surface oxide layer, which doesn't have vacancies to kind of mitigate that potential for growth of these layers, and there has to be high grain boundary diffusivity of tin atoms that can kind of diffuse towards the surface and then grow as the whisker grows. So the question is, how can we limit the grain boundary diffusivity? Like I mentioned, adding lead has been shown to mitigate this, but it's not very clearly understood what's the mechanism at play that leads to reduction in tin growth. But the challenge is lead. Since the 1990s, obviously nobody wants lead. We want to eliminate use of lead. So therefore, the industry stopped using it, and we're looking at other options to limit limit the growth of these whiskers. One of them that seems to have worked pretty well is adding a little bit of indium instead of lead to the tin. Also shows that it kind of reduces the growth of these whiskers. So the question is, why indium, and to understand fundamentally what's the mechanism at play that leads to the reduction in whisker growth when you add these atoms. So indium has about the same atomic number as tin, so that's a good thing, and it has a atomic radius that is comparable to lead, so probably it's a good substitute for lead. It's slightly higher than the atomic radius of tin, and it also has an electronegativity which is somewhat close to that of lead. So probably that leads to the selection of indium to explore the mitigation of tin whisker growth from these surfaces. So this image shows you whiskers and hillocks and extrusions on top of the surface of tin that grows out. So these are obviously as shown with the red arrows, the whiskers that grow, just imaging. Yeah.
So can you tell what are those electronic packaging systems? I've come across many times this term, but I don't know.
What are electronic packaging systems? We are talking about basically the chips, right? In any electronic system. they're on top of a substrate. You have these, the circuitry, basically the semiconducting chips, how they are packaged or put inside a, the package, the substrates on top of which you have these semiconductors that are placed silicon based. So that's what is referred to as electronic packaging, but it's not just those semiconductors. There are many different layers, and so the architecture of it from an electronics perspective is called the electronic packaging.
Basically, electronic module.
Right. So to address this challenge or question of what is the fundamental mechanism, there are, like I said, many different reasons that could be explored. One of them being the diffusion of these atoms across grain boundaries. And to simulate that, we looked at molecular dynamic simulations with which we simulated a few different systems, just pure tin grain boundaries, looking at tin grain boundaries with lead dopants added to them at a certain concentration, about 4%, and with some vacancy concentration in there as well. And we also modeled indium atoms as dopants added to these systems. And molecular dynamic simulations are able to look at the evolution of these structures with time to get to energy minimized structures, and what that does to the diffusion of these atoms across the grain boundary. So this is again an application we will look at in details after I introduce the method. So, and then the final application I'll talk about today is our work with lithium air batteries. So I already talked a little bit about other lithium ion battery. Lithium air batteries are quite different. They're actually, the chemistry is more similar to combustion chemistry. So it's almost like combustion process happening except in a battery setup. So here is a description, a schematic showing what lithium air batteries look like. So you have a lithium metal anode in this case, which is distinct from lithium ion batteries, where, like I mentioned, typically you have a graphitic anode, or more recently silicon based anode is also being explored. But in the case of the lithium air battery, you have a metallic lithium anode followed by a separator and a liquid electrolyte typically within the separator, and the cathode is porous carbon. So cathode is lightweight, which is a huge opportunity here to improve the specific energy of this battery, because it's just porous carbon based cathode instead of the layered oxide. And it's a breathing battery because you have a gas diffusion layer which breathes in oxygen from the ambient, and the chemistry is that during the discharge cycle, the lithium ionizes, and then it flows through the separator electrolyte medium to the cathode and chemically reacts instead of electrochemically with the oxygen to form various lithium oxides, lithium peroxide, superoxides, etc. And this process continues during discharge. The charging process is obviously the reverse reaction, where the lithium peroxide breaks down into lithium ion, gives away electrons and oxygen, and then it transports all the way back to the lithium metal anode and grows as a layer on top of the lithium metal. So this is how the lithium air battery works. The question is, how can we enable this or commercialize this technology? What are the challenges? The major aspects are, how do we enable quick charge and discharge? That is a very big aspect that I haven't yet talked about. For example, in electric vehicles, one of the major concerns is the charging time. How can you rapidly charge a battery? You don't want your car to take a couple of hours to charge. So that's one thing, and that depends on the electrochemistry and electron transfer kinetics that happens at the interface between the anode or the cathode and the electrolyte. The other aspect is cyclability. How many charge discharge cycles can this run without getting kind of gradually degrades, right, the components in the battery? So how many cycles before it degrades completely? And the safety, as always. So how do we map these requirements at a cell level to the requirements of the electrolyte properties? What are the properties of the electrolyte that will help us achieve that? So these are color coded. So the first one in red is the quick charge discharge. What is it related to in terms of the electrolyte property? That is related to the charge transfer kinetics at the interface. And as I'll show you, it is related to the dielectric constant of the electrolyte medium that you're using, the size of the molecules or atoms that are in the electrolyte. So those are some of the factors that determine the charge transfer kinetics at the interface. The other one is cyclability. The cyclability of an electrolyte is related to its stability domain. What is the range of voltage within which this electrolyte doesn't break down, that is, doesn't get oxidized or reduced. Oxidation and reduction means obviously we are talking about a reaction where you either lose or gain an electron and then chemically destabilize. Or perhaps it leads to the formation of certain ions such as peroxide, again through this oxidation reduction process, which ultimately degrades the electrolyte through cycles, and after a certain number of cycles the battery is not usable anymore. The third aspect is safety. So what property of the electrolyte decides what the safety aspects are? One of them is the vapor pressure. So that is obviously a thermophysical property of the electrolyte itself. And finally, toxicity. We want to make sure we are using an electrolyte that is non-toxic. So basically, the idea is how can we map the macroscopic continuum level requirements for the performance of the battery to something at the microscopic atomistic level that is related to the properties of these electrolytes, and how can we then use it to down select appropriate chemical systems that will do this job, right. So, it is important to explore novel electrolytes and how do we down select. So, to answer that, let us look at again what type of electrolytes are typically used in these lithium air batteries. The commonly used electrolytes are based on organic solvents, right. Organic solvents are also used in lithium ion batteries. The challenges with organic solvents are manifold. They have a high vapor pressure, meaning they are relatively flammable. They have a narrow stability domain. So, think why batteries do not use water as electrolytes, right, because water has a very small electrochemical stability domain. If you go beyond that, it will just break down and you can't use it. Similarly, for organic liquids, their stability window is only a couple of volts, like 2.5 volts, depending on the specific chemistry, and therefore not appropriate for a lot of high voltage battery applications, for example. And then finally, they can be toxic. So, in this particular project, to address this, we looked at in very many details one specific class of chemicals as an alternate electrolytes, and these are called ionic liquids. So, what are ionic liquids? Ionic liquids are basically like salts. Sodium chloride is a salt, so are these, except they have relatively larger cations and anions that make them, a lot of these ionic liquids are liquid at room temperature. So, they are salts that are liquid at room temperature. Not all ionic liquids, but very many ionic liquids are in the liquid state at room temperature. Because of the way they look, they are both, quite a few of them are aromatic and polar. They are great solvents. In fact, ionic liquids are used for many other applications such as carbon dioxide sequestration, in catalysis applications, many other applications for that. They have low vapor pressure, almost zero vapor pressure, which makes them pretty much non-flammable. So, it is not easy to burn these. So, they are that way it takes care of the safety issues. They are also thermally pretty stable. So, you can operate these at relatively high temperatures without these chemicals breaking down. So, that is another plus. And finally, depending on what ionic liquid you are using, they can be electrochemically stable. Not all ionic liquids, but a lot of them can operate over a wide range of voltages before they get oxidized or reduced. That is something we will look at. So, these are some of the positive attributes to ionic liquids to explore them as electrolyte. On the other hand, some of the things are either unknown or not favorable. For example, the lithium ion mobility through these electrolytes, which decides how conductive they are, which is a very important characteristic of an electrolyte, is not known, and typically ionic liquids are quite viscous. So, these are viscous, and viscosity is correlated with ionic conductivity. High viscosity typically means lower ionic conductivity. So, that could be a challenge finding ionic liquids that are relatively high ionic conductivity. And then what is absolutely unknown at that point is the kinetics at the solid electrode and the electrolyte interface. I mean, how are the charge transfer characteristics? Are they slow or fast? Because that would determine the charge discharge times, I mean how fast you can charge and discharge the battery. So that is something that needs to be evaluated. And finally, in case of these batteries, the lithium air batteries, if you go back to this slide, one of the key things is because they involve oxygen and they're kind of soaked in the electrolyte medium, one of the key aspects is this oxygen has to be soluble, highly soluble in the electrolyte, right, for these reactions to happen. So are these ionic liquids able to dissolve oxygen to a great extent? So that's something again that needs to be determined if you wanted to select ionic liquids. The good news is there are literally hundreds of different chemistries in the cations and anions of the ionic liquid, and you can combine them, resulting in tens of thousands of formulations. So you have a huge opportunity to select the right chemistry and composition to basically optimize these properties that are needed for your application. The second aspect is, even after that, let's say you do not have the desired ionic conductivity, can we add additives to enhance these properties, right? So these are two routes. Number one, tailor the combination of cations and anions to get the right favorable properties, and also explore additives. So in our work with these ionic liquids in this project, we basically addressed most of these. We'll start with the lowest length scales. So we did some density functional theory calculations to look at individual cations, anions of the ionic liquids in presence of the interfaces with the cathodes and anodes that I talked about, to get into the electron transfer chemistry. How fast does the electron transfer from the ionic liquid to the from the lithium transfer from the ionic liquid electrolyte to the anode or to the cathode in the solvated ionic liquid medium, right? So that's something that you can capture using a theory called Butler-Fulmer equation and Marcus theory. So the Marcus theory is a key theory for looking at the energetics of electron transfer between two species. So we use Marcus theory to look at this, the energy barrier for electron transfer between the lithium ion in the ionic liquid to the anode, and we can use the Butler-Fulmer equation at the continuum scale to connect that to the the current density of the battery itself. But to get into the electronic level resolution, obviously we can't use classical models like molecular dynamics. You have to use density functional theory or some sort of quantum mechanical calculation, which is what we did for that purpose. The next step up is the ionic conductivity and oxygen solubility of ionic liquids. I mentioned these are two important properties for these class of batteries, right? So we did molecular dynamic simulations of ionic liquids with and without additives, and with lithium salt added to it, to see the the diffusivity of lithium salt, to calculate the diffusivity of lithium salts in various ionic liquids, from which you can calculate the ionic conductivity. So that is very useful to feed into a continuum scale model to predict the charge discharge characteristics. We also use this model to calculate the solubility of oxygen, but to get into that, which is something I will present, we first need to introduce statistical mechanics, right? Statistical mechanics, which I'll present actually tomorrow, is basically the background theory of how do we relate so what are we really modeling with these atomistic simulations, molecular dynamics? We're looking at a system of atoms, and we are calculating their trajectory of going from one equilibrium phase to the other after the energy has been minimized, right? So we have a collection of configurations, but then what do we do with these configurations? How do we calculate properties such as oxygen solubility or mobility of lithium ions? So that connection is using principles of statistical mechanics. So what statistical mechanics does is it looks at the energy states of atoms and molecules, crystals, etc. at at small length scales. We are talking about specific energy levels that each atom and molecule in a system can occupy, the resulting configuration and energy of that structure, and then use that in a statistical manner to infer on some of the properties of that system. Could be thermophysical properties like what is the internal energy of this system if the microstates are certain, there are certain microstates that are occupied by the atoms and molecules, or what is the enthalpy of this system, or what is even the entropy of this system. Those are questions that we can answer if we know what are the available microstates in a system, and how do the atoms and molecules that comprise the system occupy those microstates, what sort of distribution we have. So, depending on what sort of atoms, molecules, or particles we are looking at, they will obey different principles of statistical mechanics. It can be a Boltzmann distribution or modified Boltzmann distribution, it can be a Bose-Einstein distribution, it can be Fermi-Dirac distributions. So, statistical mechanics is basically looking at what are the available energy, microstate energies available to the atoms, molecules, electrons, photons, etc. of a set of basically particles, and how they occupy those, and based on that distribution, how we can infer upon the thermophysical properties of that system. So, molecular dynamics simulations basically calculates the trajectories of those atoms, molecules, and then we apply a hypothesis which is called the ergodic hypothesis, which says the time evolution of these configurations, the averages you get out of that, is the same as what is called the ensemble average, which is the average of each of those configurations in that distribution. So, if it's a system is ergodic, which is typically an assumption, then we can apply the principles of statistical mechanics to the trajectory we have from the molecular dynamics simulation to calculate some of these thermophysical properties. In this case, we are talking about the oxygen solubility and the diffusion coefficient of the lithium ions in the electrolyte. Okay. And then we have a mathematical model which is called a physics-based model for at the continuum scale for batteries, which involves like I said, solving the Poisson's equation for the potential, and also looking at the charge transport through the Butler-Fulmer equation, to basically looking at species balance, right, for this system to calculate the overall performance of the battery, which is captured by the current voltage characteristics. So, I will show you in this case each of these aspects that we have addressed with our models, and how that leads from the very fundamental chemistry of the anions and cations of the ionic liquid, and scaling it all the way up to the characteristics of the battery. So, I will wait for a moment and see if there are any questions at this point. Yeah.
So, when we calculate the diffusion coefficient,
Mm-hmm.
so in experiments there are various experiments like EISC,
Mm-hmm.
GIDT and PIDT. So, when we model this diffusion coefficient, does this model use those equations like when we use in the GIDT or through CE we calculate the diffusion coefficient?
No, so this one what we use is there are a few different models for the diffusion coefficient. One is called the Green-Kubo expression, and I'll present that when I talk about statistical mechanics and thermodynamics, because it's very important in a lot of applications. So, Green-Kubo looks at the autocorrelation of velocities of the atoms or molecules, whatever in your system, and from that you can extrapolate or calculate the diffusion coefficient. Or you can also calculate the diffusion coefficient from mean square displacements. So, basically looking at displacement of each atom relative to an initial or prior location, how the mean square displacements of a certain atom or ion is relative to an initial configuration, and keeping track of that and doing the ensemble average of it, you can calculate the diffusion coefficient. But both of these are what we call the self diffusion coefficient. Yes, I will present that when I talk about MD simulation as an approach.
So, those diffusion coefficients are in electrolyte or on solid electrode, or the both?
Both. So, I'll present results for diffusion coefficient in liquid electrolytes as well as solid electrolytes, and the mechanisms are quite different.
I'm talking about the solid electrodes.
The electrodes. No, so the electrodes involve electron transport. The electrolyte is the medium through which the lithium ion transports from one electrode to the other. Once it reaches the electrode, it just intercalates, for example, in the cathode. So, diffusion coefficient within the electrode is not much of an interest, it is more like the electrolyte medium, right.
So, what should be the optimum thickness of the SEA?
Of the solid electrolyte interface. Okay, I have not talked about that. So, solid electrolyte interface, just for everyone, is, so when you start a pristine battery, there is a anode and the electrolyte that are in contact, right, which is actually quite chemically unstable, because we are looking at an ion like lithium, which is highly reactive, right. So, very soon, either by design, sometimes you add additives to make that layer form, or without design, there will be a chemical layer that forms, which is basically a mixed, like a soup of various chemicals. There are carbonates, phosphates, depending on the exact chemistry, there is a mixture of chemicals, and a layer forms on the interface between, let us say, the anode and the electrolyte, and it keeps growing. So, one of the major aspects to achieve high energy density and capacity of a lithium ion battery is to stabilize that layer. You want that layer to be there, because if the solid electrolyte interface is absent, then very quickly the interface will destabilize, but you do not want that layer to be super thick, because the thicker that layer gets, what does it do? It impedes the diffusion of the lithium ion from the anode to the electrolyte, right, which reduces the performance of the battery. So, there is a lot of work going on in terms of, number one, understanding what the solid electrolyte interface looks like, how it evolves, and how can you control the thickness and chemistry of it, because depending on that, you will have different diffusion characteristics. So, that is a good question. And so, you were asking what is the thickness? It is in the range of 5 angstroms to 15 angstroms, in that range. Is, if you could control it to that, that will be, the thinner you could get the solid electrolyte interface, it is better for the interfacial, the lower the interfacial resistance or impedance is, but it is a challenge. It is a very rough interface, it is not like a very smooth, even chemically it is very complex, it is not just one phase, it is a multi-phase and mixture of chemistries in there. So, it is very complicated.
So, when we do the model, can we see the visualization, so that the SEI is forming?
Yes, I have not modeled SEI layers, but I know of prior work, very few that have looked at the growth of solid electrolyte interface, usually using something that I have not talked about here, a reactive force fields, meaning regular standard classical MD simulations cannot model chemical reactions, because the bonds that we supply to the system are like hardwired, these bonds exist, we do not model breaking and making of bonds, but there are some specific potential models known as reactive force fields, which are able to, they are kind of empirical and very debatable how accurate they are, but if well parameterized, they are able to capture chemical reactions. And there are some studies looking at reactive force fields to capture the growth of the solid electrolyte interface, and you are right, in that sense you can see the actual growth of it, but the time scale in real life versus the time scale of that growth of the SEI layer will be off. Because remember, this is a highly non-equilibrium system. Molecular dynamics simulations makes the system evolve from one equilibrium state to the other. On the other hand, in this case, it is a very non-equilibrium system, so you cannot rely on the time scale much. But what you can rely on is the final structure you have for the solid electrolyte interface. If your force field is accurate, then that will be pretty accurate. The other approach for getting into solid electrolyte interfaces, again there is a couple of publications using ab initio molecular dynamics, but ab initio molecular dynamics you are only limited to at most 100 to 200 atoms. So, like you mentioned, what is the thickness, how it really cannot address that. It can look at very specific chemical reactions with ab initio molecular dynamics, but it cannot model very accurately the entire SEI layer. Very important question, yeah. So, for most solid state material, crystalline materials, it is not a huge deal. Basically, you have what is called a periodic boundary condition. You have a box, let us say, if you have a bulk crystal. You take the crystallographic information from CIF files, which is from experimental characterization, right? It has the lattice parameters, and you can build the crystalline system.
Yes.
And then it just replicates across all 3 dimensions, and you have a crystal structure. What becomes challenging is if there are specific defects, and if your system is too small, then there is going to be periodicity in these defects, and that might not be physically meaningful, right? In real systems, let's say you have a very dilute concentration of defects, and by periodically replicating your system, you build up, you know, you will have some defect interactions which will have some impact on the calculations. So that is one thing. Particularly if you're doing electronic structure calculations, you will see that the band structure is a big function of the defect, atomistic defects, and in that case you have to have a large enough system so that you reduce that defect interaction. So that's just one aspect. But on the other hand, if you are looking at, you know, liquid materials or liquid systems, then the size of the system is governed by, again, the chemistry. I mean, if you're trying to model a certain concentration of a dopant or additive added, then depending on whether it's dilute or concentrated, you have to choose the system size carefully to be able to sample the right system for calculating whatever property you're interested in.
Also, the time scale is the means the smallest time scale of the reaction. This time scale is also order of the 10 power minus 10. So,
Chemical reactions?
For the
Yeah, you're talking about femtoseconds or, you know, really tiny time scales, which is something you can model with molecular dynamics. Again, the challenge is, does your potential allow for bond breakage and formation? So these are called bond order potentials. So let's say you have carbon or silicon, right? So if you know the valence of those, I mean, how many bonds those atoms can form, let's say you have a sp3 hybridized carbon or a sp2 hybridized carbon. If you have that information, you can build that in as a bias term in your potential, saying that typically this carbon will only form a valence of a certain number, 4. And if it is coordinated with more than 4 atoms of another carbon, then there is an energy penalty to it. Or if it's less than 4, there is also another energy penalty to it. And you have to, basically it's a mathematical function that you have to develop that is able to push the system to have the right chemistry. I mean, that it's called a bond order potential. So if you have that, if your potential function has that term, then, you know, it's not a big deal to get into the time scales of chemical reactions.
So potential order means potential between the atomic potential between the atoms.
Yeah, interatomic potentials will have to have a certain, you know, bias towards achieving a certain valence, which will be different for each atom, right? Yeah.
So actually, in liquids, you mostly have some sort of short range ordering in the liquids.
Correct.
So can we model a system with short range ordering and the amorphous behavior of the?
You will see that from my examples. You know, hopefully, you know, I'll present quite a few examples of that, of the structure of both of liquid systems, amorphous solid systems, and crystalline systems. You know, the distinction will be pretty obvious.
We are trying to model a system which have short range ordering plus amorphous. Can we do it all together in one go in MD?
So again, the only thing you are really specifying in the MD to achieve that structure is that pair potential. So if you have the right pair potential, then you should be able to get the right structure that agrees with neutron scattering or X-ray diffraction, whatever, you know, experimental data you have. You should be able to. One option is to take a certain known potential and compare it with experimental data, or the other one is to take that function and plot it. I'll probably present some of that. And how do you tweak those parameters to kind of get the right depth of well and the, you know, basically the right curve in that potential that will lead to agreement with that experimental data. So you can fit those parameters, or you can take an established potential and try and see if it agrees. For amorphous systems in solid materials, the Buckingham potential is widely used. Buckingham type potential, I shouldn't say Buckingham potential. there's the Born-Meyer or Buckingham, which have about the same functional form. So those are very popular for modeling amorphous solid state materials with short range order or even medium range order. Yeah.
So
Other question?
regarding the ACI, one of the main concern is that it with cycling it forms, then it again breaks,
Right.
then it decomposes. So that can that be taken into account with this modeling?
Unfortunately not, because the time scale for charge and discharge is simply beyond any molecular dynamics simulations pretty much. What can be done, I'm not sure if there is any paper reporting that, is remember the SEI layer is also forming under the influence of a potential, right? In a battery there is there is a certain voltage difference which drives a lot of these processes. So perhaps applying there are you can apply MD simulations with a voltage and look at how the SEI is forming and apply a reverse potential or something like that. I'm just throwing out ideas, but you can just model the whole charge discharge cycle that is beyond the capacity or beyond the time scales that MD can model. But you can mimic those conditions in terms of the chemistry and the potential, and hopefully if you have the right potential, then it should be able to either form that layer or even break that layer.
So basically we are trying to understand the stability in terms of voltage and all those other parameters.
Yeah.
Irrespective of time.
Right. Yeah, you are just going from one structure, an unstable or energetically less favorable structure, to an energetically favorable structure under two different conditions. So the final structure you get, as long as you have the right set of potential and conditions, should agree with the experimental characterized structure. But the time it takes for that to happen is not the charge discharge cycle time. I mean, it is something else. It's not physically meaningful, the time scale.
Sir,
Yeah.
Sir, can you apply more than one ensemble simultaneously to perform MD simulation?
Not simultaneously, but one after the other, of course.
Is it possible?
So again, I haven't talked about it. I will introduce what an ensemble is for the benefit of everyone. So you're talking about the thermodynamics, right? Whether you're talking about a microcanonical ensemble or a canonical ensemble or a grand canonical. So basically, what is the boundary condition thermodynamically? Are you maintaining a fixed energy, fixed temperature, fixed number of atoms, fixed pressure? So you can do that in MD simulations. Either it's, let's say, for example, NPT, where you maintain a fixed number of atoms in your system with a constant pressure and temperature. Another one is microcanonical, which is fixed energy, number of atoms, and volume. You cannot have both together, but you can do one after the other. A lot of times that is done, which is a recipe for MD simulations to get from a energetically, less favorable system to a energetically more favorable system. That process is called equilibration. So you equilibrate your system, and equilibration is basically getting to the right state. So the methodology of it will determine how efficiently you are able to do it. So you can go through multiple stages of first start doing a canonical ensemble, then a microcanonical ensemble. That is all right, but you cannot do both together. It's either or.
What is the physical reason that the barrier arises? Like activation energy barrier, why does it arises? Means when some reaction takes place, why is the barrier arises? Is because like if we heat the material, then barrier decreases. But what is the physical origin that the atoms do not able to combine and there is a barrier?
So it's the electronic structure fundamentally. It's the quantum mechanics which determines the interaction of these atoms, and the barrier is, the path that a certain chemical reaction or an electrochemical reaction or even a transport process of an ion hopping through a medium takes. I have many examples of that I'll go over, but in going from a high energy state to a low energy state, so I don't know if you can see this slide. So basically, this is your initial energy state, this is energy and some reaction coordinate. Maybe I'll do a full screen. Somehow it's not letting me do it. So basically you're trying to go from a low energy state, a higher energy state to a lower energy state, but that pathway involves a saddle point or a higher energy state. So the activation energy is, the energy required to overcome that barrier, and the nature of that barrier fundamentally is governed by the quantum mechanics of the interaction of that atom with its neighboring short range order atoms. I mean, that decides what the barrier is.
So basically the collision between the atoms together. If they increase the temperature, the vibration frequency increases.
You are talking about kinetics.
Kinetics.
Right. So
Okay.
it's like a classic example is the energy barrier is a wall that
Okay.
you're trying to scale,
Okay.
right? There's a wall. The higher the wall is, it's more difficult to scale that wall and get to the other side, right?
Okay.
But kinetics is the number of attempts.
Mhm.
So how many times you're attempting?
Okay.
Your probability of success in climbing that wall gets better the more number of times you attempt.
Okay.
Higher temperature is kind of analogous to more attempts to climb that barrier,
Mhm.
and so that's the kinetics.
So the probabilistic
The thermodynamics is the height of the wall.
Nature, yeah. So this probabilistic nature of the
Right.
the attempt is because of the quantum mechanical description of the atoms or molecule. The jump is probabilistic.
Yeah, the jump is a function of the frequency and number of attempts, and the height of the wall is governed by the quantum mechanics of it, the energy barrier.
The quantum mechanical
The barrier
the
for that
interaction-
reaction process or electrochemical process is due to the fundamental atomistic or electronic structure, electronic interactions between the neighboring atoms in that system for that chemical reaction.
So for every chemical reaction, it is electrochemical in nature.
No, not every chemical reaction is not necessarily electrochemical.
Okay.
Electron transfer reactions would involve electrochemical reactions.
Mhm.
So, how's the best way? So, your question is, can you repeat your question?
Means when a reaction takes place, that is the ionic system. Means ions form and then ions combine with the positive ion combines with the negative ions. Then only the reaction takes place. If it is a covalent bond, then the reaction cannot take place. So I am assuming that the reaction is electrochemical, means it's governed by the
It involves some
electrostatics.
electron transfer,
Yeah.
right?
So
So, the pathway for that reaction is again determined by the quantum chemistry of that process,
Okay.
and that leads to maybe an energy barrier that needs to be overcome.
Okay.
Yeah.
So how can we determine the energy barrier? Means
There are many methods. For example, one method that I'll present here is called the nudged elastic band method, where you basically kind of guess intermediate states. But the most popular by far method for looking at chemical kinetics is called transition state theory
okay,
or variable transition state theories.
okay,
The one that, the two that I will not present transition state theory, which is used a lot in the catalysis community.
okay.
People doing catalysis modeling that, routinely do transition state theory calculations. Basically looking at many different states between the final and initial state in the reaction and coming up with the energy landscape.
Okay.
What is the energy profile between the initial structure and the final structure? That's what you're trying to get.
Okay.
That's a simple way of thinking about it. So the two methods or two theories that I will present for the kinetics, one is the Marcus theory, which I mentioned for electron transfer reactions. I'll get into quite a bit of details there. And the other is the nudged elastic band for diffusion of ions. Yeah. But there are many methods. These are not the only two. The most popular ones, like I mentioned, are transition state theory. Other questions? Okay. If not, I'll conclude the lecture today and see you tomorrow when I'll get started with the theory and fundamentals of statistical mechanics, which is basically the theory behind all these methods that I'm talking about.